So for the last video for section 4.4, I want to go through one full problem where we take a lot of the concepts we've learned now about polynomials and put them all together. And I'm also going to cover Descartes' Rule of Signs really quickly at the end. But we're going to spend most of the time working on this question. We've got the polynomial 5x to the 4th minus 4x cubed plus 19x squared minus 16x minus 4. We want to find all of the zeros for this polynomial. And then if we can find all the zeros, then we can write the polynomial completely factored. One thing that is important to note at the very beginning is this polynomial has degree 4. Remember, the degree is the biggest exponent. Degree 4 means we need to find 4 zeros. However, whatever that degree is for your polynomial, that's how many zeros there are to find. So we need to find a total of 4 zeros. We're always going to find the last 2 with the quadratic formula. Which means there are 2 left to find with this method that I'm about to show you. To find all the zeros, the first thing we need to do is make a list of possible rational zeros. And we covered this in the last video. But to find the possible rational zeros, we need our constant and we need our leading coefficient. So we've got 4. The minus doesn't matter because we're going to do plus and minus for everything. And we've got 5. And the factors for your constant are going to make up all your possible numerators. And the factors for your leading coefficient are going to make up all your possible denominators. So we want to make a list of all the factors here, just whole number factors. 1 will divide 4, 2 will divide 4, and 4 will divide 4 evenly. And those are the only numbers. And these are our possible numerators. And then for 5, it's prime, so just 1 and 5. And these are our possible denominators. And I'm going to make a list, and I'm going to go through these one at a time and take each numerator and match it up with each denominator and make this nice big list of possible rational zeros. So 1 divided by 1, that's just 1. 1 divided by 5, that doesn't simplify. I'm going to leave it as a fraction of 1/5. And then we're going to do 2 divided by 1 and 2 divided by 5, which is 2 and 2/5. And then 4 divided by 1, 4 divided by 5, that gives me 4 and 4/5. So if this polynomial has any rational zeros, it's one of those numbers. Now the long way to do this is to check every single one of those with synthetic division. But I'm going to show you a shortcut here in just a minute. But I am going to show you the long way because we are going to have to do this to get down to a quadratic polynomial so we can find the last 2. So I'm going to go through each of these numbers. I'm not really. I'm going to show you the shortcut. But we would go through each of these numbers and see if -1 will divide this polynomial evenly. If it is, then it's a 0 and we can use it to create a factor. If it doesn't, then we just throw it out and move on to the next one. So the coefficients from my polynomial at the very beginning were 5, -4, 19, -16, and -4. And we're going to go through synthetic division and see if -1 is a 0. Remember, -1 is a 0 if the remainder is 0. That was our the combination of our remainder theorem and our factor theorem from the last section. So pull the first number down. Multiply, add, multiply, add, multiply, add 20, 30, that's -44, and then multiply, back to positive, add, we get 40. Remainder of 40, that means x equals -1 is not a 0. And we just go on to the next one. Now I'm going to try +1. Same coefficients because we haven't found any yet. So first one comes straight down, and then you multiply and add, multiply and add, multiply and add, multiply and add, and we have a remainder of 0. That means x equals 1 is a 0. Now we need to find 2 of them with this method. So we would go on to the next number in the list and try it. You also, I suggest, should try that number again, because remember, we can have zeros with multiplicities. That means they work several times. The trick is, though, once you find one that works, you are now going to use these new coefficients to continue your problem. I have already taken my 5x to the 4th minus 4x cubed plus 19x squared and divided out one that works. And our goal is to get down to a quadratic. Well, if this original one was a 5x to the 4th, and I divided out one of my zeros, these coefficients down here represent a polynomial that's 1 degree smaller. So it's going to be 5x cubed plus 1x squared plus 20x plus 4. That is the polynomial we have left over, and that now has 3 zeros, and that's because we have 3 more to find. So I'm not going to go through my list to find the next one. Let me write these coefficients over here. 5, 1, 20, and 4. That's what we're going to work with from now on. The shortcut is to remember that zeros and x-intercepts are the same thing. So you could type this polynomial into your calculator, and I'm going to type the original one, 5x to the 4th minus 4x cubed, that one, and see where I have x-intercepts, because the x-intercepts and the zeros are always going to match up. So I've got 5x to the 4th minus 4x cubed plus 19x squared minus 16x minus 4. And I'm going to do zoom option 6, which is the standard window. That's always what I use to graph to start with. And it looks like we have got 2 of them. They're really close to the origin. So since I see two x-intercepts here close to the origin, I'm actually going to zoom in, and I'm going to change my window here. And instead of looking -10 to +10 in both directions, I'm going to do -4 to +4. And that will zoom me in a lot closer to the origin. And then hit the graph button. So it looks like this polynomial crosses at +1, which is perfect because we just showed with the math that 1 works. So it makes perfect sense for us to look at this graph and see that it's crossing at 1, because the x-intercepts are always going to match up with the zeros. And it looks like I have another one over here just to the left of the origin. And I'm going to ask the calculator what it is. So I'm going to go to second trace, which is my calc list, and I'm going to ask it to tell me that 0, which is option 2. And it's going to take me back to the graph, and it's going to ask for a left bound and a right bound. It wants a little region to look in for the 0, and then a guess. And it says this other 0 is -0.2. Well, -0.2 is the same as -1/5. And guess what? -1/5 was on our list, and it should be, otherwise we've done something wrong. So I know right now that -1/5 is going to work. So I don't need to go through and check every single one of these. I know that -1/5 is going to work. So to speed up this process a little bit, I'm going to do -1/5 next. And even though we know it already works, and I know I'm going to get 0 back, we need to reduce this down to a quadratic so we can use quadratic formula. Right now it's a cubic. So if I take another 0 out, we'll be down to a quadratic, and we can just use quadratic formula for the last 2. So first number comes down, and then we multiply, and we add, and we multiply, and we add, and we multiply, and we add. And we get a remainder of 0. I knew that was going to happen because we looked at the calculator and saw that -1/5 was an x-intercept. That means -1/5 will be a 0. And what we have left down here, the last number is always the remainder, But these other three numbers represent the coefficients for a quadratic because it started off as a cubic and we pulled 1 out. That's going to reduce our power by 1. So these numbers here represent the quadratic that's left over when we divide them out. So this is 5x squared plus 0x plus 20. And once you're down to a quadratic, you can use those as your a, b, and c in the quadratic formula to finish this problem out. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And we need to simplify that as much as possible. So that's not going to matter. We've got plus or minus the square root of 4 times 5 is 20. 20 times 20 is 400. So I've got 0 minus 400, which is negative 400. And 400 is a perfect square. And the negative is going to come out as an I. So we have positive or negative 20i over 10, which simplifies to plus and minus 2i. So these are our other two zeros. So we can make our list of zeros. X equals positive 1 and negative 1/5. Those were the rational zeros. And then we also found positive and negative 2i. And those are complex zeros. And if this polynomial had any complex or irrational zeros, this method wouldn't work and we would have to find them with quadratic formula. So the way I do it is I always just use quadratic formula for the last two. So this answers part A. These are all 4 of our zeros. And we can take each one of them and use it to create a factor. Because if x equals 1 is a 0, then x minus 1 is a factor. If the 0 is negative and we subtract it, it's going to change to a plus. And this actually is 2 of them. It's positive 2i and negative 2i. And we have to do x minus for each of them. This is not my final answer because I don't want to leave a fraction in one of the factorizations. What we're actually going to do is we're going to take that denominator and pull it to the front. So my final answer for the factorization is x minus 1 times 5x plus 1 times x minus 2i times x plus 2i. And that is f of x completely factored. And we get that just by finding those zeros. And I'm sorry, my camera keeps pausing. So I have to switch it off for a second, turn it back on, and it will show you. But you can hear my voice, you can't see the the factorization I did, but there you go. So the last thing I want to do really quick is show you Descartes' Rule of Signs. It doesn't really solve anything for you, but it does kind of narrow down how many positives and negative zeros your polynomial could potentially have. So Descartes' Rule of Signs says, first of all, look at your polynomial f of x. And count the number of times that the sign changes between positive and negative. Your list of zeros is going to have that many or a multiple of 2 less positive zeros. And then create f of negative x and look at the number of sign changes. And this is how many negative zeros we could have. So when we had that big list of rational zeros to check, we could possibly narrow it down and say, oh, there has to be 2 positive and 1 negative. So really quickly, I'm going to do a short one. X cubed minus 2x squared plus 5x minus 9. So when I look at my f of x, I have positive, negative. That's going to get counted. That's a sign change. Negative to positive, that counts. Positive to negative, that counts. So for the positive zeros, I can have either 3 or 1. You can subtract 2's.